Same thing going backwards. There's more of them, right? This is approximately sine 5x. This is a real rough sketch. And what I want to know is what is happening as I approach 0, right, from the left. So go to that curve, which is the compressed sine curve here. Let me take the black one out here. And I want you to get onto that curve and approach 0 from the left. That means you're down here, right? And you're headed up towards, here's 0, x coordinate of 0. You're coming in on the curve from the left. You are going to be headed towards 0, right? From the bottom, which means these are all little negative values, aren't they? Yes? So that means that the bottom, I know it's going to 0, but I can tell you it's going to 0 through negatives. So I know this is headed to 0 through negative values.
It's negative infinity.
So negative infinity is your answer. What if I had changed this to a plus? You would be coming in from the right, which means you would be coming into 0 on this side and coming down, and those are all approaching 0, right? Y coordinates are approaching 0, but they're positive. They're above the x-axis. So that would be positive, and therefore your answer would be positive infinity.
So if you would ask, what's the limit of x?
Just to 0 without the plus or minus does not exist. Is that okay? All right, you're going to have to just mess with the homework. There's not a whole lot of stuff in the homework that deals with this. I think there's one problem, and I think I do it in my video.
Is there examples that you could possibly give us?
Well, did we talk about how this book is like not my favorite?
Yeah.
That's part of the reason why, because like these trig ones, there's only 2 in the whole section in the homework set. There's only 2. So, I mean, and I think I do both of them on the videos, so that doesn't leave you a lot. You know, I'll try and find some. Maybe if I find some, I can send some out. Yeah. All right, let's move on to the next topic, which this was, what was this called? Infinite limits. What was happening was that we were taking a limit and we were getting infinity. We were getting infinite limits. Now we're going to talk about something called limits at infinity. Please also reference the course video that you were supposed to watch before you came here. Remember that with the things we just did, right, where your function is going to infinity or negative infinity, those correspond to vertical asymptotes. Vertical asymptotes occur where our functions do that, what we were just looking at. Now we're going to look at limits at infinity, which corresponds to horizontal asymptotes. So again, watch the video, I'll talk about that in there. Here, all limits that limits at infinity look like this. Limit x goes to plus or minus infinity of f of x. So the big difference here, the big change, is that up to this point, we've always let x go to a number, right? A, x go to 2, x go to negative 3, from the left or from the right. Now what we're doing is we're saying, what happens to this function if I let x just get arbitrarily large? Or really, really, yeah, we should talk about that. What do we mean by that?
Really, really negative?
Yeah, this is a good discussion to have. Would everyone agree that if I go out that way, I'm going to get a very, very large number? Yes? If I go out this way, am I going to get a very, very small number?
Well,
We've always been told that the greater numbers are to the right, lesser numbers to the left. So this is just a language thing. We have to make sure we understand each other. If I say in this class a very, very small number, I'm talking about a number close to 0. If I want to talk about that, I'm going to say a very big negative number. Right? That way there's no confusion. So I don't want you to think of this out here as being a very small number. I want you to think of a number close to 0 as being small. 0.000001, that's a small number. Negative 1,376,000, whatever, that's a very big negative number. Think of it as like a distance from the origin. So our language is all consistent, that good? All right. So when we're looking at this and we're saying what's happening to our function as x gets big, I'm either going to have a positive infinity here or a negative, not both at the same time. It's either going to be just this or it's going to be minus, one or the other. That just says, hey, go to the function, here's your function, and tell me what happens as you go out this way. Does the function ever head to something? And that's what we called horizontal asymptotes in college algebra. Does it head to something or does it not? It may not. Think of a parabola, right? Parabola. As you go out to the right, does it head to anywhere? No, it just goes up to infinity. As you go out to the left, does it go anywhere? No, it goes to infinity. So you don't have to have a function do anything, but sometimes they do. And we need to know how to determine that. And that's what these limits allow us to do. This is really just asking us to find the left and right end behavior of a function. What's happening on the left side? What's happening on the right side? All right, let's do an example. And we've all seen the infinity symbol, right? Like we're comfortable with this. Is infinity a number? No, it is not. Infinity is an idea, that's right. It's the concept of letting something grow without bound. Just continues to grow. You can never get to infinity. So here comes your first example. I'm going to take the limit as x goes to infinity of 1 over x to the n, where n is equal to 1 or 2 or 3 or any of these. What's the answer? 0. This was what I was hoping you would have known when you walked in today. All right? And in my video, I show you different functions, and I show you what happens as you go to the right. They all go to 0. But think about it in a number sense way. Your top is fixed, right? Your top is fixed. I'll do a specific example. That's too general. Let's do the one on the quiz. Okay, what's happening here? The top is fixed, right? Top's going to 1, it's fixed. The bottom, infinity cubed. Well, that's just a big number times itself times itself. That's a huge number still, right? So this is still infinitely large, getting infinitely large on the bottom. So if you take a number and you start dividing it by a huge number, that ratio gets smaller, and this should go to 0. Agreed? That's what's on your table. I handed this to you. Bottom right corner. And does it really even matter if the top is positive or negative? Like say you have a negative number up here. No, a negative number divided by a very big number is going to be a really small number. Right? Negative or positive, it's still going to 0 no matter what. Is 0 positive or negative? It's neither one, right? So if you're headed towards 0, it doesn't matter if you're coming in through positives or negatives, you're headed to 0. So this is a big deal. We need to remember this right here. Anytime we have fixed number over something that's becoming infinite, that goes away. And now we can do a more interesting problem. Something like this. What's the limit as x goes to infinity of x plus 7 over 3x minus 5? So tell me about the numerator. Something getting infinitely large plus 7. Still big? Still infinitely large? Okay. Over something getting infinitely large times 3. Even bigger. Minus 5. Got a little smaller, but does minus 5 really make a difference? Take 5 away from infinity. I think it's still going to be big. Agreed? Infinity over infinity. This is the first time we've seen this, right? How do we deal with this? According to the table, what must I do? Some sort of algebra, some sort of trick. So there is a standard method, okay? There's a standard procedure, and here's what it is. What we're going to try and do is use that thing that we just wrote down a second ago. We're going to try and use this. We're going to try and do this. The fact that when we get fixed over infinity, that goes to 0. We're going to try and utilize that. Right now, I don't have any of that. I have infinity over infinity. So I'm going to be very clever right now, and I'm going to create those situations in this expression. So I'm going to write down limit as x goes to infinity. I'm going to leave a little space in the front. I'm going to write down what I have here. And this is what you're going to do. You're going to look at the denominator. You're going to look at the highest power of x that you see. X to the first power, right? And you're going to try and make that x vanish by multiplying through by something that'll make it cancel out. So I'm going to come in here and multiply the bottom by 1 over x. Do you agree that if I multiply the bottom by 1 over x, that first multiplication through will turn it into a 3? And the x will be gone. Yes? But I can't just do that. Whatever I do on the bottom, I have to do on the top. So you're going to just have to throw that upstairs also. Now that is a legitimate move for me to make. Algebraically, it's allowed. I can put a 1 in there. The only thing I have to consider here is possibly the fact that, what if x was 0? I couldn't do this, could I?
Yeah, that's what I was thinking. I was like, well,
Yeah, what if it's 0? But look where we're headed. We're not even close to 0, right? We're way out the right side of the graph. So I'm not worried about any undefined parts. So it's okay to throw that in there. So now distribute, 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 and let's see what the remaining expression looks like. What is this first multiplication through here? 1. Next one? Plus 7 over x. Over 3 minus 5 over x. So where I used to not have any of these situations of fixed over infinity, do you see that I've created them? See how I've created them? 7 over x, 5 over x. If I now let x get really big, this right here is going to go to 0. Right? And this right here is going to go to 0. When I take the limit, when I let x grow now, those are going to vanish. And what's left? 1/3. That's your answer.
so it doesn't matter what x is doing, basically.
It does matter that x is going to infinity, because that's what tells you that this is going to go away. Like if x was going somewhere else, this wouldn't go away. It's the fact that this is growing without bound. 7 fixed divided by something that's growing without bound will go to 0.
Oh,
Got it?
okay. Because then it's just 1 plus.
1 plus nothing, and that's going to go to 1, and the bottom is 3 minus nothing, basically, and that's getting closer to 3.
Why?
Yeah. The further you go out, right, the bigger x goes, the less significant this term becomes, eventually to the point where it's totally insignificant. And so our function is approaching 1/3. Am I going to ever get there necessarily? No. Could I? Yes. There are some functions where you will achieve your limit, but it's not guaranteed. All right? I can give you an example, if we have time, of a function that we approach a value and we actually do achieve it. It's kind of weird. It's going to be we call it a dampened sine function, yeah. But that'll be if I have time. All right, so we came in, we were clever, right? Does anyone remember from college algebra that when you had a rational function and you wanted to know what the horizontal asymptotes were, which told you what happened out the left and right hand side? Do you remember them telling you that you would compare the degree of the numerator and degree of denominator? And if the degrees were equal, was this special case. If the degrees were the same, which they are here, your answer is just the coefficient of this one divided by the coefficient of that one. You remember that? That's it right there. This is it with calculus. Okay?
I remember that.
That's your horizontal asymptote. So if someone's asking you for the horizontal asymptote from now on, they're really asking you for the limit as x goes to infinity. That's what they want. But see, in college algebra, we were limited to just rational functions. Now this applies to any function. We can do this too. All right, let's do another one. How about x goes to infinity? Let's do a quadratic, because you like quadratics. Or you know what? We'll do a quadratic on the top over a quadratic on the bottom also. Or no, let's do a cubic on the bottom, and I'll keep it clean like that. There we go. X is going to infinity. This is going to infinity, right? 3 times infinity squared, plus infinity again, minus 1, doesn't matter, right? That doesn't make a difference. It's headed to infinity. You okay with that? You agree? All right. Same thing with the bottom. Infinity cubed plus 1, still infinite. So they're both going to infinity. That's a problem. We have to figure it out. Well, I've only done one example like this, and so what I told you to do was look at the denominator and identify the highest power of x, which in this case is this right there. And you need to make that go away. So what am I going to have to divide it by to make it go away? X cubed, right? So I'm going to do a 1 over x cubed out in front of it. Whatever I do the bottom, I must do the top. And that must pass through everything. Limit x goes to infinity. All right. What do you get across that top? 3 over x. That's your top left. What's the next term up there? 1 over x squared. Last one? 1 over x cubed. Good. Bottom. 1 plus 1 over x cubed. Right? Just multiplying it through. All right. That's supposed to help. Let's see if it does. X is going to go to infinity. What do we have here? Fixed over infinity. Fixed over infinity. Fixed over infinity. Fixed over infinity. Plus 1. So what do we have on top? 0, right? 0, 0, 0. They're all going away. 0 over 1 plus 0. That's okay. This is just 0 over 1. That's just 0, and that's it. We're done. The limit is 0. We're headed towards 0 as we go out the right side of this graph. Now, let's back up. You know how I've been saying that the technique is to grab your highest power of x down here and get rid of it by canceling it out? Notice that if I always use that method, if I always use that train of thought, then this guy right here, when I multiply through with whatever it is, this guy will never go away. It won't be a 0, will it? Right? It'll always be a 1. Or if there was a 3 in front here, it might be a 3 or something, but it won't be 0, will it? Everything else, I wouldn't care if everything else went away. I don't want anything, I don't want the denominator to ever be 0 though, do I? And that's why I pick I go to the highest power down here, I make it go away. I know that no matter what after that, this guy won't be 0, the denominator then won't be 0. and I shouldn't have a problem anymore. That's why we do it. Right? Everything else went away in this problem, but this guy stayed here, and that saved us right here. It saved us from division by 0 again. All right, college algebra, do you remember this? This was also a rational function. Look, let me just erase these. That would have been a rational function in college algebra, and they would have told you to compare. If you're trying to find the horizontal asymptote, they would have said compare these. And they told you that if the degree of the numerator was smaller than the denominator, that the x-axis was your horizontal. Well, the x-axis is y equals 0, isn't it? So we would have known it would have come out like this. And that's exactly what we just got here. And any time you have a polynomial over a polynomial, if this degree is bigger than everything else, then when you divide this one out by the x cubed, all the other ones are going to be fixed over infinity because they're all smaller. I don't know if you're seeing all that. If you are, great. If not, just follow the method. But there's kind of a bigger picture, I guess, to this all. What would happen if I flip this over? Was that it? Flip it over. It'd be infinity over 1. Let's see it. That's correct. Let's do it though. What would you come through and multiply the front and top and bottom by here? 1 over x squared. 1 over x squared again. Why? Because I'm looking at the highest power of the denominator so that I know that when I multiply that through, that one's not going to go to 0. Limit, x goes to infinity. What do we have here? That one. X, and then plus 1 over x squared. Bottom left, 3 plus 1 over x minus 1 over x squared. And almost all of them go away, right? Almost. This one fixed over 0, fixed over infinity, fixed over infinity, fixed over infinity. Those are all gone, but what's still there? X over 3. If I let x go to infinity now, those are all getting squashed away to nothing, right? That guy is growing without bound. He is blowing up, right? And there's nothing there to offset him. I'm dividing him by 3, big deal. Take infinity and divide it by 3, it's still infinite. So this thing is blowing up. It's going to infinity. It's actually it's growing linearly. It is linearly. I know it seems like it would be fast, but it's growing linearly because this is linear. But yeah, so you can get an infinite answer. And back in college algebra, again, they told you if the degree of the numerator was bigger than the denominator, you would have this thing called a slant asymptote, oblique, or something like that. Okay, and you could use long division to find it. I know in my college algebra we didn't focus too much on that. Yes? In the denominator. That's the key. In the denominator. Good question. Yeah, because what would happen, that's perfect. Look, what if we had done cubed? Cubed, cubed. What if you had gone after that one right there? Yeah. You would get a 1 on top, great. Plus 1 over x cubed, fine, that's going to 0. This would be 3 over x, right? When you come through with 1 over x cubed. This one would be 1 over x squared. And the last one would be 1 over x cubed. Do you see the problem now? That goes to 0. 0, 0, 0. You now have division by 0. Not good. So we just don't do that. Yeah, then, well, actually now you're back at, no, you're at fixed over 0. Right? Which is what we did before this. And then you'd have to analyze that and figure out what's going on. But I would avoid that. No, just stick to the rule of thumb that I gave you. All right, so you think you understand what you're supposed to do as far as looking at the denominator and figuring out what to come in with? Okay? All's good? Okay, so now we have stepped away from college algebra. This is not a rational function. So you can't follow any of those shortcuts in college algebra. You have to do this one with a limit. Bless you. This is probably the last one we're going to be able to do. We'll see. Check it first. What's happening? Numerator? Getting really big. Denominator. Just look underneath the radical first. X to the fourth plus x minus 5. Let x get big. This thing's huge, right? Square root of infinity? Still infinity, right? It's still big. So we have that situation. Yeah, okay, so let's go with the same method. The same method was we got to get rid of that x to the fourth, right? Highest power we see in the denominator. The problem is that whatever you come in with has to be a 1, right? And it has to start out here. You can't put a 1 over x to the fourth in the root, because where are you going to put the part that offsets it? The 1, the part of it that's up top. You understand? You can't put it in here. It's got to be out here. 1 over x squared. Why 1 over x squared?
Because you're actually taking the square root of x to the fourth actually x. And it would also get rid of the square root.
Yes, that is correct. Let me try and explain so everyone understands, maybe just a different perspective on it. Look, anytime we've seen square roots, right? If I had like x cubed, I think most of us hopefully we're comfortable with the idea that that's x squared times x. And then because you're taking the square root of x squared, you could essentially like pop an x out. Yes? Pop one x out and you have x still left in there, right? We all comfortable with that? Yes?
Isn't it just the same as writing x to the 1/2?
This would be, yes, yes. But everyone's okay with that. All right, I want you to think about it this way. Let's say you have this expression and I tell you, I want you to push that x back in to the root, which you normally never need to do. But what if I tell you to push it back in? What happens as it gets pushed in? As it goes into the root, it gets squared on its way in. Because it's a square root, you square it on its way in. If you had x cube root of x, and I told you to take that x and force it back into the root, what would you do? You'd cube it on its way in. And this would become cube root of x to the fourth. Yes? Okay? All I need you to take from this is that if you have something outside of a root and you want to push it in the root, it's got to get squared on its way in. Well, if you have something on the outside of a square root and you want to push it into the root, it's going to get squared on its way in. Is that all right with you? Okay. So when I take something and I push it through here, it needs to become squared and become 1 over x to the fourth. Right? That's what I need it to be. So I'm going to use 1 over x squared. And 1 over x squared. So think about it. If I take this and I push it into the root, when I square it, I square the top, it's 1. I square the bottom, x squared squared, x to the fourth. So that will give me what I need once it gets in there to cancel things out. Now, I know there's other ways I could have explained that might seem clearer to you, but I'm thinking long term, there are some other things you may see later on down the road where you're forcing things into roots, and I want you to look at it as you have to square it on its way in if it's a square root. Cube it if it's a cube root. Sixth power if it's a sixth root. I think that's more valuable if I show it to you that way. But all right, you ready? Top one, just that's it, right? Just pass it through and we're good. So top is 3 over x plus 1 over x squared. Bottom, let's go ahead and force that 1 over x squared into the root. It becomes a 1 over x to the fourth, and it's sitting in there, right? It's there now? It just went in. But next to it is x to the fourth plus x minus 5. So you still have to distribute that into each of these. I mean, we're almost out of time. Are y'all okay with that? Yeah? No? You don't like it? You don't like it?
I like the word like teacher taught me, where like I can just have all the square root.
You could do what?
Like instead of going like what you just did,
Uh-huh.
I see it,
Mhm.
you can just go x squared plus x 1/2 minus x 5 to the 1/2.
Wait. X. You can't do that though, because it's addition between the terms, not multiplication. You can't break this into square root of x squared plus square root of x minus square root of 5. You can't break that, because it's addition and subtraction. Y'all don't like me right now. Okay, look, 9 times 3, 27. Square root of 27 is square root of 9 times 3, right? Okay, this is 3 root 3. Because what you did is you took the square root of 9 that came out as a 3. Now I'm telling you, put that 3 back in. I didn't want it out here. So when you put it back in, it has to get squared and become the 9 again. That's what we're doing. But we're saying to ourselves, I want x to the 4th to go away, so I need a 1 over x to the 4th out here, but it has to start out here. So when it goes in and I square it, it's got to turn into what I want. That make any more sense? Okay. All right. Yes, I'm going to finish. Now, what happens? We have limit. X goes to infinity. I haven't taken the limit yet. I'm just trying to figure out what the hell's going on here. So, square root. Let's see. Pass that through. What do we got? 1.
Plus 1 over x3 minus 5 over x.
Yep. And a lot of that's going to go to 0. In fact,
Square root of 1 is 1.
So it's 0, 0.
yeah, that's 0, that's 0, that's 0, that's 0. So we're getting 0 on top. I'm a little concerned. Not really, though. The bottom is root 1. The answer is 0. Yes?
Why don't you just square top and bottom and then do it right there?
The question is, why don't I just do what? Square the top and the bottom to get rid of the root.
Then you have to factor out the top.
That's a good question. What do y'all think? The question was, why don't I just square the top and the bottom? This is absolutely a great question, because I think I asked the same question. I don't think I had the nerve to ask it in class, but I think I probably had the same question. Look, if the root's causing the problem, why not just square it? I mean, that always saved us in the past, right?
Yeah, that's why I was.
Right? Why not just square the top and the bottom? Great question. Well, here's why.
So I was thinking maybe you could like use substitution or something, and then substitute the bottom for u, and then square it, and then put it back in, but then
Yeah.
some method.
Okay, so let me ask you something. If I take the number 3 right now, everyone agrees that's 3. If I square this right now, is it still 3? No. It is not, right? I mean, of course, 3, sorry, square. That is true, but what I started with was 3, and by me squaring it, I no longer have 3. All right? Now, if I give you an equation right now, and I tell you x is equal to 3, you are allowed to square both sides of the equation, and that would still maintain the relationship I have between x and 3. Well, we actually introduced an extraneous solution here because of this, but I can only square both sides of an equation. You cannot take an expression. You cannot take an expression and just arbitrarily square it. If you do, it is no longer that expression anymore. It's not the same thing you started with. So the only way to undo it would be to square root it again. And so you'd be right back where you were.
But you could
Yes.
multiply it by that same thing, by like square root of x to the 4th plus x minus 5 over the same thing.
Yes, you could do this on the top and the bottom of the exact same thing. Right? Is that what you're saying? You could, that algebraically is okay. The problem is that's not going to save you in this problem. It's not going to help.
So basically, that's a much more powerful.
The way I'm showing you, trust me, I'm not trying to show you the hardest way to do this. I'm trying to show you the most efficient way to do it, and this is what we have for this situation. Come through, find the highest power of x on the bottom, figure out what it takes to make that vanish, and go from there. All right, so do your homework. Have a good holiday weekend, right? I'll see you on Tuesday. Try not to wipe the brain cells out completely.